Great.
It's 4 o'clock in Miami. Welcome, welcome, welcome. Thank you for coming. Bob, thanks for coming. We've done all of this so Bob could be here. We're very glad to welcome Stephen Collins today to speak, and he'll be speaking on opportunities in cloud engineering. And it's interesting, you look at his bio, and it's just a who's who of the communications industry and networking. It's pretty wild. He earned his bachelor's degree here in 1981, and then he went straight to Bell Labs in New Jersey, and then they sent him off to grad school at Michigan, where he earned his master's degree. And then he went back to Bell Labs, and he did some work at ARPANET. I don't want to tell you too much because he's got all kinds of details about these things, but not at ARPANET, but worked on ARPANET technology at BBN, Bolt, Beranek, and Newman in Cambridge, Massachusetts. He was part of Wellfleet Communications, a very early communications company, and a VP of many different things at Active Broadband Networks, Acme Packet, Sonus Networks. He'll probably tell you more about a big project he had, which was purchased by Lucent, which was a variant off of Bell Labs, right, Lucent?
Well, yeah, Lucent was the old Western Electric plus Bell Labs.
Okay.
Yeah.
So it's a real privilege to have Stephen Collins here, so let's welcome him.
Thank you, Baird, and thank you for asking me out to do this. I really enjoy, first of all, getting out to campus when I can, and I really enjoy engaging with students and faculty out here. I was thinking today when I was driving out, it was actually 40 years since I first ventured onto campus here at UMass Amherst, so it's been a little while. But I've really enjoyed keeping in touch over the years and watching the university as it grows and evolves, and obviously very exciting today with all the construction going on here, so that's a wonderful thing. So what I'm going to talk about today is essentially the opportunities that I think are going to be presented to graduates of the university in the area of cloud engineering. So I'm going to talk about a lot of technology, but this isn't a technical talk. So if you have a question about a particular technology that I referenced, don't ask me. Go ask your faculty or your favorite grad students or somebody. I might know the answer, but there's also a very good chance I'll be completely stumped. So feel free to ask, but I'll be completely blunt if I have no idea what I'm talking about. But my goal here is to essentially talk you through what's going on in the cloud. It's just fundamentally interesting and exciting. And for someone like myself who started his career in computer engineering, when I look at where we've come in the last 40 to 50 years to where we are today, it literally boggles my mind. I mean, I literally am just kind of stupefied by what's going on around me. It's why I keep working. A lot of people say, well, gee, why aren't you retired? And I said, well, started playing golf again this summer, and I was really awful at it. That's one reason why I'm not retired. But more importantly, I just enjoy doing this stuff, and I like sharing it with people. So I'm going to kind of talk through what's going on in the cloud and try to shed some light on it. From my background and experience, everybody can get a copy of this. You can look at what I've done on LinkedIn. You can look on my website for my consulting business. Today, I do work as an independent consultant. I spent a lot of my career working in smaller companies, startups, fast growth companies. Spent a little time at Bell Labs back when AT&T was like the biggest company in the world, I think. We had over 1 million employees back in those days. But most of my career has been kind of on the leading edge of network and telecom technology, and typically with smaller companies. I've worked with some bigger, faster growing companies, but typically smaller companies. And today, as an independent consultant, almost all my business is with smaller companies. Kind of bare bones startups to 10 million in revenue. I don't even think I have a client that's doing 50 million in revenue. So I'm typically working with the folks that are, taking technology innovation and bringing products to market. So that's a little bit about me. Probably my biggest claim to fame is back in '98. I co-founded a company called Springtide Networks. We were a unicorn. We were bought for over $1 billion. and we barely had a product shipping. So, things go in cycles, I guess, right? 20 years later, we have unicorns. But we were a unicorn back before there was a name for that. And my career I started as an engineer. I spent 10 years in the trenches doing mainly software engineering on communication systems. And then I kind of transitioned over to kind of the product management, product marketing, and then ultimately more senior executive roles. Mostly what I've done has been involved in the go-to-market side of the business, which is, marketing, product marketing, business development, supporting the sales operation, things of that nature. And I kind of tend to do that today as a consultant. That's kind of the work I like to do. I could probably still write software, but I don't do that anymore. So what I'm going to talk you through here is kind of a whirlwind tour through the cloud, but I think this will hold together and make sense. I want to start off with just giving you a brief historical perspective on how network computing has evolved over the last 50 years. And then, I'm going to give away, spoiler alert, right? The cloud is the computer, right? That's the trick today. This thing we call the cloud, which is a virtual entity, that has become the computer. And it will continue to be the computer for a huge array of applications and services. Then I'm going to kind of talk through the stack, talk what's going on from an application level, kind of the supporting infrastructure for the applications, what's going on at the network layer, because there's actually a whole transition taking place at the network layer. And I want to touch a little bit on big data, machine learning, and AI, because that's actually where a number of my clients play today. So I actually do work in that area. And then really want to give people a feel for what the future challenges are. I mean, if you look at the size of Google, Facebook, Amazon, the Microsoft Azure cloud, I mean, these are ginormous companies with huge operations they've implemented in the cloud. But I'd argue we're still only in like the first inning. And I want to talk about that towards the end. And then I'll wrap up by kind of enumerating the possible kind of career avenues for people. And they are numerous, right? I mean, I don't think there's a single avenue that you couldn't take if you found something you were really interested in. This is, I think, really exciting stuff. So many of you were not even born yet, I think, when this was a slogan for this company called Sun Microsystems. So this dates back to kind of mid-90s. Sun had a marketing slogan, the network is the computer, and they built some of the first networked workstations, right? So these were basically machines that interconnected on an Ethernet and connected to a server. It's what I did all of my software development work on when I was an engineer at Wellfleet Communications, building some of the very first multi-protocol routers. And they had this vision statement, the network's the computer. And at the time, I think it was largely aspirational. But I think if you look at where we are today, this has kind of become true, right? Most of our computing capacity is in the network, in the cloud. And we didn't really talk too much about clouds back in the mid-90s. This is sort of a fun slide. So if you look back, wind all the way back to, say, the 1970s, which is basically when I started college, we did have network computing. And the network was the phone system, which was a wonderful network. And you could do anything you wanted on that phone network, provided it involved making a phone call, because that's all that network did. And so we figured out how to hook up computers to the phone network with these gadgets called modems. And I think earlier today we were having lunch, we talked about acoustic couplers, where you'd actually pick up a phone, make a call, get a audio signal from the other end, and then plug your phone into the acoustic coupler, and your terminal was talking to the host over that connection. But we really only had one network, and it was run by the AT&T, the Bell System Network. And that's actually where I started my career, was working for AT&T inside of Bell Labs. And there really was one dominant computer architecture back in those days. It was IBM's Systems Network Architecture, which was a terminal to host architecture. So you were taking these 3270 terminals and connecting them via these modem connections back into the host, which usually resided in a big data center somewhere. And this was kind of the state of the art in 1975, maybe through the late 70s. And then we had this thing back in those days called time sharing. So if you wanted to get access to computing power, you could actually go to a company and purchase time on one of these big mainframe computers to run your applications. How many people have heard of serverless today in the cloud? Anybody heard of serverless? Yeah. So serverless is something Amazon offers, Microsoft offers. It's basically a way of just running code in the cloud and just getting charged for, how much time and resource your code consumes when it executes. It's essentially time sharing. So in some respects, 50 years later, we've almost come full circle. But I don't want to belabor this. What I think is really interesting is right around the same time this kind of network computing paradigm was peaking, a bunch of very sharp engineers gave birth to this thing called the ARPANET, right? And this was funded by DARPA, and it was a very large-scale packet switching network, which had its genesis in kind of the very late 60s, early 70s, and by the mid to late 70s, they built out this nationwide network entirely for research purposes, mainly universities getting connected. And they would basically connect host computers over that phone network using these things called packet switches or routers. In the ARPANET, they call them IMPs, or interface message processors. But this was a revolution because this is what validated the whole concept of packet switching, and it's what gave us the entire kind of TCP/IP protocol suite, which is the foundation for all the networking we do today. So this was kind of a major event. I was fortunate, as Baird mentioned, back in the mid-'80s to actually work on these systems, to work on these routers when I was with BBN Communications. They were still fairly primitive devices then, but that was actually the thing that kind of opened my eyes to the whole world of computer networking, and it's why I ended up joining on as one of the founding engineers at Wellfleet Communications, and we were building routers competing directly with Cisco. And this is before anybody knew who Cisco was, or knew who Wellfleet was, or even knew what a router was. So it was very early days in the networking business. So if you look at this, the networking computer evolution, I've broken it down kind of by decade. This isn't an exact timeline, but roughly this is what happened, right? We had this whole mainframe computer model that I just described. Then we had the PC revolution, right? So now you could put a computer on your desktop, and then shortly thereafter, people figured out, well, I could take these things called local area networks, and I could connect those computers together, and I could put a server out there somewhere on the network. So that was kind of the big thing that happened in the 1980s. And then what happened was the internet was born, right? And that was a direct outgrowth of that work that was done at DARPA. So now we could take all these kind of desktop server networks and we could interconnect them over the internet and over also these private wide area networks that businesses were building out. And that's kind of what we did at Cisco and what we did at Wellfleet, right? We took routers and we built out the public internet as well as private wide area networks. And so that was a tremendous wave of technology innovation that took place during the 90s. Then you get into the 2000s, and what did? We went mobile, right? We had the mobile device explosion, and we had at the same time the fixed line broadband explosion, right? We could deliver multiple megabits over a connection into the home or a business, and we also went increasingly mobile. So that's kind of what happened in the 2000s. And then if you look over the last decade, I'd argue we're kind of in the cloud era. And we're in the era that everything's becoming available as a service. That's why I have XaaS there, right? So you look at most of what we consume as consumers, right? Whether it's entertainment, gaming, content, e-commerce, right? All of that stuff is now being delivered to us typically as a service, via this cloud infrastructure. So it's really amazing when you look back at how this developed, say, over the last really roughly 50 years. And now what I want to do is kind of drill down into where we are today and what this whole thing looks like here, this whole cloud scale infrastructure and everything as a service. So we're at the world today where the cloud is the computer, right? And you have people building absolutely gigantic data centers around the world to support this cloud computing. Pick photo on the right? I don't know where the heck that was taken, but that's what it typically looks like inside of these data centers. Amazon's building them, Apple, Facebook, Google, Microsoft, IBM, and Oracle, amongst others. And then there's a bunch of big Chinese companies that are building them out as well, and in other parts of the world. But this is kind of what the computer looks like today. It's got cooling, right? That's a big problem, right? They have to figure out a way to get rid of all that heat that all those machines are generating, right? They consume massive amounts of power, so they have to put them in a place where they got access to some sort of power source, hydroelectric, nuclear, what have you. And then they're just filled chock full of servers and switches and storage, right? So that's kind of the world we're living in. And the question becomes, how does this whole mess operate? And how do we put all these pieces together, and how do we turn it into something that's useful? So if you look at what's going on, think about all the different applications and services that are moving to the cloud and have moved to the cloud, right? So you've got Amazon e-commerce, Google search, you've got bazillions of websites, you've got all the big social media players, streaming audio, streaming video, mobile apps, software as a service, gaming, communication services. This whole IoT thing is going to be absolutely huge, right? That's going to be kind of another layer on top of the cloud, because not only will you have these, I think, big data centers that are more centrally located, I think we'll start to have distributed data centers that will support the operation of these IoT applications. And then you have the public cloud providers that offer these infrastructure as a service and platform as a service. This is the whole host of services that like Amazon, Microsoft, and Google offer. Those could be database services, machine learning services, all the kind of ancillary services you need when you're going to develop an application. There's a whole host of them. You go to the Amazon website, Google website, they'll show you what they offer for services. And then we still have private data centers, but those are turning into private clouds. What I mean by private cloud is they're using the same type of building blocks to construct the private data center. The data centers we've built to date, typically, the private data centers are kind of classic, what are called three-tier data centers. The data comes in, it hits a load balancer. Load balancer directs that to a web server. The web server is going to handle those transactions. It'll go back to an application server, and that might reference some data sitting on a database server. But the data kind of comes in and goes out traveling what's called north-south through the data center. These new kind of cloud hyperscale data centers don't operate that way. There's actually a tremendous amount of what they call east-west traffic, and it's because of the way the applications themselves are being structured. I'm going to talk about that. So whether or not you use public cloud services or still implement things in your own private cloud, you're going to be doing it off the same core technology, the same building blocks. And I'm going to talk about what those building blocks are. So the fundamental challenge is, how do we move all this stuff to the cloud? If you look at what's going on today, sure, Amazon, Microsoft, Google, Facebook, Apple, they built their clouds out of necessity. I mean, how do you serve millions or billions of users? Well, that's what they did. They went off and solved those problems. But if you're a business, you're a big global 2000 company, Fortune 500 company, and you want to move your stuff to the cloud, is everything there that you're going to need to do what you currently do in kind of your private data center operations and your private network? Will you be able to move that to the cloud? The answer is, in some cases, yes, and in some cases, no. And that's what I want to talk about towards the end. There's still a number of challenges, despite how massively scalable this stuff is today. It may not be quite ready for prime time in terms of putting real business critical and mission critical applications out there. Largely to do with issues revolving around kind of availability and security. So I'm going to touch on that as well. So these environments that we end up using to operate in this kind of cloud mode, they're highly complex. If you look at this, right, we've got users out here. They could be remote users traveling around using mobile devices. They could be at home. They could be in a business. They could be out in some far-flung remote office or branch office. There's all this stuff up in the cloud that they want to use that I've simplified into 4 little clouds there, but it's basically all that stuff I just had in the last slide. And then you have all this network connectivity in between to get from here to there. It's super complicated. There's a whole bunch of stuff going on here from the endpoint here to the application running out there. And there's tons of stuff you no longer have control over, right? You know, you're relying on some sort of internet transport that you hope is going to work. You're relying on a service that one of the providers might be offering you. You may be relying on a content distribution network to kind of get the content that's in the cloud out closer to you so you can access it more readily. Whole bunch of stuff. There's a lot of moving parts in all of this. And I would say this is kind of the challenge, and it's also from the perspective of people like yourselves coming out of school, this is also the opportunity. How do we kind of scale this up and make this work in a really robust, reliable, and kind of secure manner? I just wanted to touch on this because this is actually a slide that I use in the work I do as a consultant. We use this for some work I'm doing with some companies in this organization I'm involved in. It's a really good way to kind of conceptualize kind of the full extent of what's going on here. And how is all of this put together? So what are sort of the key concepts, and what are the building blocks, the piece parts for all of this? And I want to spend some time touching on this. So first and foremost, from a conceptual perspective, the big thing about the cloud is a lot of this technology is very open. It's not to say you won't find proprietary technologies being deployed out there, but the idea is things are opened up. And when I say open, I don't necessarily mean standard, but I mean that you can program to it, or you can hook your application or service into it, or you could hook your device into it. So the idea is these aren't closed systems, they're not proprietary systems. There's no sort of artificial barriers that are going to prevent you from running your software here or running your software there. The concept of openness is kind of fundamental to what we're doing in the cloud. It's also very disaggregated. So things that used to be monolithic, and I'd say monolithic, I could be talking about application code, or I could talk about a particular type of device, a switch or a router, or even sort of special purpose devices you might find in computing centers. There's been a lot of purpose-built hardware, software systems developed over the years. What we're doing now is kind of tearing them apart and not delivering things as monoliths, but well, we have a part of this thing that does X, and a part of it that does Y, and a part of it that does Z. So let's productize those three things separately, because it gives us the flexibility to do some mixing and matching, and also allows us to use very low-cost hardware that we can drive the price down and get sort of commodity scale pricing on some of those key elements. So disaggregation is another concept. Virtualization, so this is the notion of something that was sort of a tangible physical thing. You could point to a box and a rack. Those things are going away. The function that box and the rack might have performed is now typically done in software, and that could be kind of floating around out there in the cloud, right? And it can be positioned where it needs to be positioned. So a good example of that is like a network firewall. You used to think of a network firewall that always sat in the DMZ, the demilitarized zone, between an enterprise network and, say, the public internet. Put a firewall there. It's almost like a physical thing that's protecting your perimeter. Well, when you move to the cloud, you got stuff running in the cloud, you got to take a virtual firewall and stick it up in the cloud where your stuff is running. And that's how you protect what you're doing in the cloud, right? So this concept of virtualization is kind of part and parcel of what we do in the cloud. Everything is software defined, right? So the whole notion is we're not trying to kind of build purpose-built hardware that does functions X, Y, and Z. We're going to really try to define the functionality of this infrastructure in terms of software. And there's a big concept here that you'll hear people use called infrastructure as code, which basically means I want to operate all of this stuff using a set of open APIs that I can program to deliver whatever I need to deliver via the cloud, whether it's an application or a server, service, a mobile app, something like that. So everything becomes very programmable, and that ties back into the concept of openness, right? Another big piece of this is instrumentation. You got to be able to keep track of what's going on. Think about that huge data center with thousands of servers and switches and connections. You need to have instrumentation so you can get visibility into what's going on, so you actually know when something bad is happening. So one of the things you'll hear people talk about in those hyperscale data centers is not just east-west traffic flows, but you'll hear a phrase used called elephant flows, which means all of a sudden a massive amount of data is moving from this server here to that server over there. You may not have any idea why, but that's kind of gumming up the works because it's bottlenecking sort of those network connections that are running between the servers within the data center. You got to know that, and you got to be able to get visibility into that so you can take some sort of corrective action. And so there's these two kind of go hand in hand, right? The instrumentation lets you kind of drive telemetry that you can then ingest, and that gives you this thing called real-time observability. And you'll hear this term observability used a lot in the context of kind of cloud-based operations. And what that means essentially is I can figure out what's going on without necessarily having direct control or even direct telemetry over every last piece of the puzzle here. But if I can observe this and if I can observe that, I can infer that something's going wrong over here. And it's sort of a concept that actually goes back to like control system theory, actually. But if you Google observability, you come up with all kinds of interesting articles about this. And I actually spend a lot of my time in this world. Instrumentation, telemetry, observability, because it's kind of like the new thing. But it's being driven totally by necessity. These systems are operating at such scale, such levels of complexity, that it's just a fundamental challenge to keep track of what the heck's going on. And then what kind of goes hand in hand with this ultimately is these concepts of orchestration and automation. They're related concepts, but they're different. So automation is anything you can do to just have the machine do what a human would do. So everybody's familiar with things like scripts, right? You want to get the computer to do X, Y, and Z, you can write a script for the computer to do X, Y, and Z. There's a tremendous number of automation tools that do that in the context of the cloud, from the application layer right down to the network layer. Orchestration's a related concept, but orchestration says what I'm doing consists of multiple domains, and each of those domains might have their own center of control, and they might be running various scripts that are automating things within that center of control. What orchestration says is I want to kind of coordinate all of that. I want to make sure, well, we do this over here, we do that over here, we do that over there. It really is like a conductor, telling the violins to play loud and the horns to play soft. It's a concept of coordination and automation that spans multiple domains. And this is a really important thing because you're trying to put applications in the cloud. Well, you've got the application code itself. You've got the services in the cloud. You have to put that code up there in the cloud. There's a whole kind of deployment aspect of this. There may be network things you have to do to support those new applications that you're putting up into the cloud. And there may be things you're doing in your own private cloud as well, because you might have to connect them back and forth. So the notion of orchestration is all the kind of mechanisms that have to be invoked to do something like that. I mean, both of them boil down to things that people would sit there in a computer and do manually, and getting the machine to do it automatically. And I'm going to show a slide here shortly, and there's just a tremendous amount of work going on in this area, just again because of the nature of the complexity and the nature of the scale. From a building block perspective, the nice thing about the cloud from a hardware perspective is there's a lot of commodity hardware being leveraged, right? So Intel, multi-core, CPU-based servers, right? I mean, racking and stacking them, thousands of them, right? And some of these now can have up to, I don't know what the latest number is, 32 cores in the latest Intel server class CPUs, I'm not sure. But these things have, massive processing power. Low-cost disks, increasingly flash storage as opposed to disk. From a switching perspective, from networking perspective, the real big change here is moving towards what's called merchant silicon. So these are still ASICs that do switching functions, but they're kind of sold into the commercial marketplace, and anybody could build a switch out of these chips, as opposed to companies like Cisco or Juniper or Alcatel-Lucent, who build routers out of their own kind of custom design silicon. There's a big trend towards merchant silicon switches. Another big trend is GPUs, so the graphic processing units that we now have in PCs, right? Turns out these are wonderful devices for doing this massive parallel processing that you need to do when you do certain machine learning algorithms. So those are being deployed as machine learning engines. Very expensive hardware still, very specialized obviously, but becoming increasingly important. All this stuff is based on kind of the Linux OS and that whole Linux OS ecosystem. That's a big part of it. A mess of programming languages, kind of Python's kind of like the hot one you'll hear being utilized a lot for certain operations, but there's a whole host of programming languages. And then there's a kind of a massive amount of open source software that's come into play. And I'm going to touch on that. But the open source software communities are becoming increasingly important for a lot of the stuff that I talked about over here, as well as just kind of the fundamental way the software actually executes in these cloud environments. And I'm going to touch on that when I talk about things like microservices and containers, if you've heard those terms being referenced. So before I kind of dive in, I just want to kind of step back for a second and look at this. So the cloud's a wonderful thing, right? There's all these benefits that we get by kind of moving things to the cloud, right? So we get performance. We can get performance at the scale we need. We get elasticity. So, you want to deploy your mobile app. You start out, you get 1,000 users. Then you have 10,000 users. Then you have 100,000 users. That thing's going to scale up. It's going to be very elastic. You can even do that automatically with an Amazon. It'll essentially auto scale. Cost you more money, but you can auto scale. So you don't have to sit there and go, oh my God, we just got 10,000 more customers. What are we going to do? It just happens. They just basically give you more capacity in the cloud. You get a lot of flexibility. It's inherently resilient infrastructure. I don't want to say it's perfectly resilient, but the fact that it's based on kind of a distributed computing paradigm, you've got some inherent resiliency there. And then words like agility, which just means, I can do things really quickly here because I'm not dealing with monolithic pieces of code or monolithic hardware, software systems. I'm just dealing, hey, I want to do something, I can tweak this and I can tweak that, deploy it, and I'm done. So you move very quick. And then it's open, talked about that. And, relatively speaking, it's cheap. I mean, these data centers that are getting built out are billions of dollars, but if you look at them at a cost per bit basis, it's about as low as you can go. I mean, all the big players build their own servers and build their own switches. I mean, that's what they're doing. They basically design their own equipment. They don't buy anybody's stuff unless it's some new and different thing that they just haven't gotten around to doing themselves yet. But with all these benefits come a whole host of challenges, and this is kind of really what I wanted to alert people to, because I think engineers like challenges, right? These are problems that still need to be solved. First is just the massive level of complexity that's involved. This stuff is still highly complicated, and it's not getting any simpler. And it's due to the fact that it's multi-layer and multi-domain. You've got stuff going on at the application layer, the infrastructure that supports the applications, the network layer, and then you've got stuff happening, from the user side, through the transport network, into the cloud network, up into the cloud provider's services, and then whatever the heck you're running on top of those services. So you've got a lot of different kind of domains or spheres of control, and you have a lot of different kind of layers that things are touching on. And the whole mess is distributed, right? You could be running stuff in a cloud that's physically here or physically there or both at the same time. You may not even care. It could just be kind of happening for you just based on choices you might say, if something scales up over here, fire some workloads up over here and support what's going on over there. It's not quite that dynamic nowadays, but that's kind of where we'd get to. The whole thing is very dynamic too, right? So that's the other thing about this. Clouds are constantly kind of expanding and contracting based on application load, based on user demand. The whole mess is highly disaggregated, like I mentioned before. And then you have an amazing degree of choices, right? From the technologies you want to use, maybe the software you want to use, the suppliers you want to select that software from. These are all kind of the challenges, or I'd say the kind of the flip side to the benefits. And so there's no shortage of kind of opportunities here in trying to make some of these challenges go away. And that's what really kind of makes it ultimately expensive. OpEx is operating expense. I'd argue that the good thing about Amazon, Facebook, Google, Apple, they're massively profitable companies. So they can afford to manage this stuff. They can wrestle it to the ground. You know, your average, you know, Global 2000 business can't, right? So stuff has to be simpler for them and easier to manage. Now this is looking at what I'm going to call the multi-cloud infrastructure stack, kind of from top to bottom. And I broke it down into kind of 3 layers. There's a layer at the top that really deals with the application software itself, and I'm going to call that the DevOps layer, because the DevOps is this new paradigm for how we develop code in kind of the cloud native world. I'm going to talk about that, I think, in another slide or two. Then there's a layer in between. I'm going to call that the system layer. So that's the layer of the most of us are familiar with computers, right? That's your operating system layer. You have these concepts called virtual machines these days. You got the fundamental computing and storage capacity. And then you have the network layer. And I already talked about some of the things that are going on at the network layer. There's this concept of network virtualization that's going on that's really interesting. Networks are becoming increasingly software defined. And when I say software defined, again, that implies some principles of disaggregation being applied, as well as the notion that these networks are becoming more programmable. So you can make the network behave in a way that's appropriate for whatever application traffic it's supporting. And then a really cool thing I'm going to touch on is kind of programmable silicon. This is becoming, I think, a big deal. And it's really exciting if you're a software engineer or a hardware engineer, what we're going to see happening going on right down at the chip layer. So we got kind of 3 fundamental layers here, and I'm not going to talk at all about security because that's a whole world unto itself, but security is like a really, really important thing, and it needs to span kind of all layers and all domains. And that's all I want to say in this talk, because we'd be here for another 3 hours if we were going to talk about security. So what I'm going to do is kind of quickly kind of touch on each of these kind of layers in the stack. So there's this thing called Cloud Native DevOps. I was just last week in Boston at a conference. It was called DevOps Days Boston. And this is kind of a organization, operates around the world, where people that are kind of DevOps practitioners kind of put together their own community events. So this is a cool event to go to, because I had a lot of the folks that are in the Boston area who kind of do DevOps for a living. And what is DevOps? Well, DevOps is sort of an approach to writing software and kind of a methodology, right? So the approach is what I've listed here, which is the notion of taking what were once kind of monolithic software applications and breaking them down into their kind of constituent piece parts, which we typically call microservices, which says, you know, in the old days, you'd think of it as being almost like a subroutine, right? But, you know, I take a microservice, this thing, I interface through it this way, it gives me this response back. It could be managing some data. And what you'll do is, rather than having this big monolithic application that manages all of this stuff, you'll break it down into individual microservices that can be deployed where they need to reside in the cloud. And so big companies like, say, Airbnb, Uber, right? When they're deploying their software, they're using this methodology. They're deploying software in terms of dozens, hundreds, perhaps even many hundreds of microservices that they're deploying to the cloud. And not just deploying, but constantly redeploying. So there's a notion here of what's called continuous integration, continuous development. You're constantly doing what's in that loop there. You know, you're building the system, you're coding it, you're planning it, releasing it, monitoring, operating it, deploying it. Really, you know, so sort of this continuous cycle that you're constantly engaged in. And the benefit of this is you've broken things down into small microservices that, you know, maybe a team of 3, 4, 5, 6, 7 people work on. And they're very focused on that microservice and deploying that. And they can do this daily, weekly, whatever frequency needs to be done. And everybody's kind of doing this in parallel. And what you achieve is, you know, much faster kind of time to market for things where you have to do an update, right? Rather than have to update the thing and do a massive regression test on a huge monolithic piece of software, you just say, well, you know, gee, we wish it would kind of interface this way over here. Let's just modify that microservice here and that microservice over there, and you're done. And they can spin that stuff and deploy it rapidly. The number of deploys per day that goes on in some of these cloud native operations is pretty wild. I've heard numbers like hundreds of deploys per week, for software that's being kind of modified and deployed. Now, some of that could be very trivial stuff. You might just be changing how a web page reads, but some of it could involve some more, involve logic and manipulation of data. So I don't want to, we could spend all day talking about DevOps, but it's a really big thing. And it's something that I think, students should be exposed to, certainly in school. And there's no shortage of resources out there for those who are curious about learning more about DevOps. But I think this is a real, revolution in software methodology. It ties right into the whole agile development model, that's been popular now for a number of years. But it's more than just agile. It's a whole, it relies on sort of a whole fundamental infrastructure. The word that I haven't touched on yet is this notion of a container, because typically what we do is we take microservices, we implement those by writing code that resides in a thing called a container. So a container is a more fine-grained execution entity in the operating system. And the notion is here they're a little more lightweight than like I say, a full-blown virtual machine might be running under VMware. And the cool thing about containers is you can spin them up and down on demand, right? You need more capacity for this microservice. You just spin up more essentially identical pieces of code in additional instances of that container. So it's a way you kind of auto scale. This was all driven out of necessity, developed at Google. A lot of the original kind of adoption of this was kind of driven out of necessity. You think about what these guys are doing. They had to figure out a way to kind of build in auto scaling into their systems. Google and others, I should say, not just Google. So at any rate, this is a big deal. I think it's really cool, and it's starting to find its way now into the enterprise IT market. Most of the practitioners of this are the big web scalers. It is like the Airbnbs and the Ubers of the world. But this is starting to now move into kind of mainstream, Fortune 500 IT shops as a way to kind of do business. And there's a whole host of tools and runtime software associated with DevOps, right? So I just pulled a couple of graphics here. There's an organization called the Cloud Native Computing Foundation. Good place to start if you want to learn about DevOps tools and runtime software. This is the home for this thing called Kubernetes, which, like I said, had its genesis at Google. It's now kind of open sourced and out there in the public. And then look at, there's a whole set of tools that get used to kind of work through that cloud native DevOps life cycle. And that's just a partial list. But it's a really interesting thing to explore. And if you leave UMass and go to work for some company in, say, Kendall Square in Cambridge, you're going to be doing DevOps if you're writing software. I mean, 90% certain that's what you'll be doing. So let me transition down a little bit to the kind of the supporting hardware infrastructure in these cloud scale operations. The hyperscale data centers have a very specific architecture. And the architecture is based on a really simple proposition. I've got racks and racks and racks of thousands of servers, but they built out the network architecture in such a way that any server can kind of directly talk to any other server, with the minimum number of hops through intermediate switches. And they do this with a very specific kind of switching model, which is sort of a two-tier model that has what's called leaf switches, which sit at the top of the rack and interconnect all the servers in the rack. And then you have spine switches, which are used to interconnect all the racks with all the other racks. So it's kind of a full mesh of connectivity. The net result is if I got a server here, needs to talk to a server over here, it can talk to that server kind of, with the least number of hops, right? You don't have to kind of bounce around to kind of get from one to the other. And the way they actually implement these physically is they build out pods. They're kind of pod-based designs. So they actually have you could think of this thing as sitting on a pallet. It's got a bunch of servers, it's got a bunch of switching hardware, and hey, gee, we're getting run out of capacity in this data center, just go to the warehouse and bring them out, drop the pod in, hook up the cables, and guess what? You just got more capacity. It's very clever. It's like a cookie cutter design in terms of how they scale these things out. You could spend a whole week of your life, I think, understanding the nuances of how that works. But it's, I think, a really cool way to kind of build out this massive scale, but do it in a very kind of normalized fashion. So you can, no matter where you are in the data center, everything's going to kind of look the same. So what I had mentioned earlier is what we're seeing inside of these data centers, because we've broken things down into microservices and we have them operating in these containers that can be spun up and down dynamically depending on load and demand, what we end up with is a whole mess of traffic that's bouncing around inside the data center. So that's why we say that the east-west traffic is flowing this way as opposed to the stuff that's coming in and out of the network. And today, in most of these big data centers, 80% of the traffic is actually flowing east-west just between servers and the data center. And only 20% is actually going outside the data center, you know, whether it's to the internet or wherever the devices are that are using the applications that are running there. So it's really a fascinating kind of turn, because the old data centers, it was really exactly the opposite. Most data was coming in and out, very little was bouncing around inside the data center. Now it's been kind of entirely flipped on its head. But this is also a real challenge, right? Because I think it's messy. You know, you really don't know where your stuff might be running inside of some cloud operator's cloud. They might not even know where it's running, right? And, you know, let's say you suddenly have a lot of demand and some stuff gets spun up here. All of a sudden there's a bunch of data flowing back and forth. That's maybe competing for network bandwidth internally with some other data flowing back and forth. You get conflicts, you get bottlenecks. It gets really messy. And I will tell you this, I know that the data center operators who are building these out are still working on the tools so they can get visibility into this stuff at a level where they can see it fast enough to know what's going on and fix the problem. It's always easy to figure it out, you know, after the fact, you know, in a forensics analysis, but how can you figure it out on the fly when it's happening? Briefly on network disaggregation, I don't want to hammer home on this, but I spent a lot of my career building things like this. Big monolithic switches, routers, other types of devices, custom ASICs, FPGAs, network processors, building them in different form factors. You had usually had the big box, the medium box, and the little box. A lot of proprietary software, tightly integrated hardware and software, which means sometimes I can't release new software until I get the new hardware released. Typically, development cycles are like on 6-month increments at best. So you want some enhancement, you know, and it's January, you might not see that enhancement until July. And if you miss the July window, you might not see it till next January. So, you know, this is kind of the world that we've operated in, particularly network equipment. And, you know, high risk of obsolescence too. You buy one of these big things and then, you know, 5 years later, it's a boat anchor. The new approach is, let's use off-the-shelf hardware, servers, switches, commodity pricing, mass-produced by folks like Dell, amongst others, and leverage merchant silicon, standard form factors for racking and stacking this stuff, putting software on top of this that's kind of this open software-defined networking software. You've decoupled the software from the hardware, so if you want to rev the software, you can do that without having to worry about the fact that I'm running this switch or that server. And you get sort of a high degree of investment protection. I mean, eventually the switches and servers will get old and you will have to upgrade them, but you might get a longer shelf life out of them than what you would out of something like this. So it's fascinating what's going on in the network world. And this is just kind of starting to happen, right? This is going to be something I think is going to take 5 to 10 years to kind of play itself out. But it's already happening inside the cloud operators' big data centers. They're already doing this stuff. Out in the corporate networks, a little bit less so. But I think it's an inevitable trend because of really all the benefits I've listed on the right-hand side. And if you want to learn more about open networking initiatives, there's a whole mess of open source projects. There's folks developing new protocol standards. There's a mess of software-defined networking stacks and APIs out there at kind of different layers in that realm. A lot going on with, like I talked earlier, about network virtualization and virtualizing network functions. Those are kind of two different concepts. Network virtualization is, I have like a TCP/IP network, but I'm going to run another network on top of that. And one of the things we're doing in the wide area network today is we're building what's called SD-WAN, so software-defined wide area networks. And that's a way of running like a private enterprise network over the internet. So it's still a TCP/IP network underneath, but we've built sort of a secure overlay network on top, typically with encrypted tunnels. It's typically how you do that. So that's a type of network virtualization that's taking place. The other thing is network function virtualization, which I touched on earlier. Take a physical firewall and turn it into a piece of software that you can kind of deploy anywhere. And there's a whole bunch of that going on as well. And security appliances, the security business, there's about, a dozen different security functions you need to support. Usually people build dedicated appliances to support them. Those are all being virtualized. I'm not so sure anybody will sell a dedicated security appliance unless there's some throughput requirement that requires specialized hardware underneath. And there's a lot of open hardware specifications being developed by this Open Compute project. They're kind of speccing kind of common specs for servers, for switches, and they do other things too. They have some very interesting work they're doing in high performance computing. If anybody wants to go down that detour, it's interesting. So, and then there's a bunch of stuff going on with programmable silicon that I want to touch on as well. And this is one of them. So this is a really cool thing. This is called P4, and there's a website called p4.org, and it's a way of doing programmable packet forwarding, essentially at the microcode level in a chip. So you can buy a networking chip, but you can give that networking chip a particular set of capabilities based on the application that it's going to be used in. So a good example of that would be, if I'm doing a security application, I may need to look at very specific places in the packet, and I may need to look for very specific fields and maybe correlate them with some other information to figure out that something bad is going on. Well, guess what? I could actually load a special load of microcode into that chip, so I can create a custom packet forwarding pipeline that's specialized for that security application. And so this is programmability at the silicon level. You wouldn't do this on the fly. It's sort of a boot time thing. You're going to load that microcode in, but you can personalize that chip to say, hey, this is going to be a great chip to put in a security appliance that might be doing denial of service attack detection and protection. Or, hey, I want to use this thing to do maybe some type of communication systems processing where I have to have very strict quality of service or something like that. So I want to touch the packets in a certain way or inspect them in a certain way as they kind of move through the chip. So you can basically code that forwarding path at the silicon layer and do it in a fairly generalized fashion. This was initially commercialized by a company called Barefoot Networks, and they were just acquired by Intel in the last, I think, 6 months or so. So it's a very cool concept, but it just tells me we've gotten to the point with the silicon where we're actually going to be able to do programming right down at that level. So you can build a more generalized chip and then kind of give it a personality based on application or purpose. And a company called Arista Networks, which builds switches, they actually built a switch that's based on like such a chipset. And they sort of sell it as a switch that you can say, hey, look, I want to use the switch for X, Y, or Z, and they'll load a different load of microcode into the chip, sort of give it its personality. It's a very cool concept, but it just shows you we now have the additional cycles available in the silicon because of the speed at which the silicon's able to operate to do these types of things. These things would have been unthinkable, I think even 5 years ago. So this is a really cool thing. Actually, I think the professor that did a lot of the work on this was a Stanford prof, if I'm not mistaken. His name escapes me right now. But I want to shift gears entirely and talk a little bit about big data, machine learning, and AI. And all of these things are big. They're a big deal. You hear about big data all the time. You probably hear about AI all the time. And I don't think the importance of these technologies can be emphasized enough. It's certainly hyped, but this is a case where I think the hype is kind of justified. All of this stuff really kind of has its genesis in the cloud. All the big guys building out these big hyperscale data centers, they all had big data problems they had to solve. So a lot of the core big data technology was open sourced and came out of places like Yahoo and Facebook and all these guys who are building out this massive scale application infrastructure. And today they all have major initiatives in big data, machine learning, and AI, all of them. I mean, any of these guys, go to their website, look at what they have available for services. And it's because the cloud is sort of an ideal environment for doing this. It's inherently distributed. You got scalable processing capacity and storage, so you don't have to really worry about, well, how much big data do I need? Storage for it's there. You need more, it scales kind of automatically for you. So it's highly elastic and scalable, and it's resilient, right? So again, just due to the distributed nature of the cloud itself, it's going to be more resilient than if you just kind of had sitting that in a corner on a server in your own data center. And there's a whole host of open source technologies and turnkey services that are available for big data analytics, machine learning, and AI. And the one thing I will tell you is there are not enough people in the world that know how this stuff works. And that's a problem for the big guys who are doing it every day, the companies that want to try to leverage this technology. We have a critical sort of industry-wide skills shortage for people that understand how big data, machine learning, and AI stuff works. It's so bad, right, that the big guys, Google, Facebook, Apple, even Amazon, they went off and hired like literally entire departments out of universities. Right? They went in and just took the AI researchers and said, hey, come and work for us. And the guys said gladly. And the amount of money some of these people are getting paid, coming out of grad school with a degree and some specialty related to machine learning or AI, they're getting big bucks. So it's certainly an excellent area to go off and work in, and I think probably could be quite happy working in this for the next, 10 to 15 to 20 years. It's just hard for me to imagine this kind of capping off anytime soon. And then there's a really cool thing going on, which is at the hardware layer, there's a whole bunch of acceleration technologies being developed to support kind of the machine learning and the AI stuff. So I mentioned earlier, you got the GPUs, which are being used because they have massive scale parallel processing, right? You can essentially run a whole mess of code threads in parallel through a GPU. So you got, guys are actually building dedicated GPU-based platforms for doing machine learning. You can actually get a big box that's chock full of GPUs, and then they'll actually put that on the network, and you can load your workloads into it and execute your machine learning and download your results, or you could rent the boxes. I've run into these guys at trade shows. It's actually quite cool what's going on. So this is a big deal. But then there's, I stumbled across this in my wanderings. At Facebook, they've developed a bunch of different kind of special purpose hardware accelerators for different types of AI and machine learning applications. So, if you're a hardware designer, don't think all is lost because everything's going to the cloud, and if I don't want to do cloud programming, I can't do anything. No, I think we're going to see a whole renaissance at the hardware layer to support what's going to go on in the cloud. Because it turns out, despite the fact that these Intel processors are loaded with cores and they can execute at multiple gigabits, they're not well suited for certain types of algorithms. And so I think we're going to see kind of a whole new renaissance here at the hardware layer to support what needs to be done for machine learning and AI. So that's super cool to me, right? Because it kind of comes around full circle. You have software innovation that's going to drive more hardware innovation. Another piece of this is FPGAs, right? So field programmable gate array. So this is basically a way you can build a big honking chip that's going to do certain types of hardware-based functions and do it in a programmable fashion. So you can, turn around the code overnight with an FPGA, whereas an ASIC, you don't do that. You build an ASIC, you design an ASIC, goes to the foundry, you get the chip back, there's a bug, you're toast. With an FPGA, you go back in the lab, change some code and basically burn a new FPGA and you're back in business. The FPGA thing is kind of coming back to life too. I think there was people thinking, well, that thing's kind of run its course, and it hasn't. Intel went out and bought one of the two big FPGA manufacturers, not Xilinx, they bought the other one, I'm just blanking.
Altera?
Yeah, they bought Altera, right. So, and I talk more and more with hardware developers who are like, well, we're doing an FPGA for this and we're doing an FPGA for that, simply because the performance requirements are such that you can't keep up with an Intel-based CPU architecture. So there's still a ton going on at the hardware layer that's really exciting, and there's tremendous opportunity for people to come in and participate in that innovation. One of the last things I want to talk about, though, is, so where are we going with all of this? And I think the next frontier, in my perspective, is what I'm going to call kind of mission critical multi-cloud. Not to say that what we're doing today with all those applications and services I put up there before, not that those things aren't mission critical, but for most of them, nobody dies if the cloud goes out of service, right? You know, you don't get your Uber, you can't access your Dropbox, you can't order new dog food on Amazon. I mean, these are all bad things. I can't stream Netflix. Actually, in my house, that would be an emergency. I take that back. But, you know, think about it. Most of the stuff we do using the cloud today wouldn't be the end of the world if we couldn't do it. When you start looking at applications for IoT, and particularly like healthcare, where you're trying to monitor patients that might be at home, right, or monitoring seniors who live alone at home, the whole industrial IoT piece, where you're using IoT to kind of manage and monitor industrial processes in real time. Or, this is even scarier to me, you have smart infrastructure, right? So this is the smart car, smart city, you know, smart whatever. You know, that's where if there's accidents, you know, people could get hurt, people could die. So how do you take all of this and move the supporting applications and infrastructure, you know, to the cloud-based model? Well, it's got to be ultra reliable. It's got to be low latency, because you can't have, you know, any delay in terms of both the service delivery as well as just knowing if something's going off the rails. And it's got to be super secure, right? And so this is, I think, kind of the next frontier, is moving the cloud in this direction. Not just kind of business critical multi-cloud, which I would say that's sort of taking enterprise IT and moving it to the cloud. I'm talking now mission critical multi-cloud. And so again, you know, this is totally ground floor. You get into this, you're getting in on the ground floor. Despite the fact that there's massive hype about IoT and a ton of vendors already in the space, again, I still think it's really very early days. Most IoT today is getting the right sensors, figuring out what data they spit out, what the heck do I do with this data? You kind of feed that up a stack to, you know, the supporting applications that are going to feed off of that data. All that stuff's been kind of worked out. But if you want to move that onto kind of a cloud scale infrastructure, I don't think that's been worked out yet. But this is where we're going to head. I mean, I think you're going to look at big industrial corporations potentially building out maybe their own special purpose clouds for doing some of this. It might not be the Amazon cloud or the Google or the Microsoft cloud as we know it. Might be built off of the same kind of building blocks. Might even be operated by those guys, but it might be its own separate beast. So this is, I think, really interesting. I kind of talk about this a lot in kind of my travels. Sometimes I think it kind of goes over people's heads, but I think, you know, I tend to have a disease where I like to think out 5, 10 years. And I think that's kind of, you know, where I'm looking with this stuff. I think 5 to 10 years out, we're going to see that. So kind of wrapping this up and taking it back to, you know, what's an opportunity for a student coming out of an engineering program today. I kind of have a grid there on the right-hand side you can kind of look at, but there are no shortage of opportunities, whether you want to play kind of at that DevOps layer, you want to be kind of a developer. There's other DevOps roles where they call them like site reliability engineers. So those are the people that kind of make sure the trains are running on time. A whole bunch of different roles. You might even wear different hats and operate in different roles during the course of a week. That's the cool thing about DevOps. You might not just say, I'm just a developer, I'm just a site reliability engineer. You might depend on where your team is in your little continuous integration, continuous deployment model. You might be wearing different hats and operating in different roles. Maybe you want to do that. Maybe you want to develop the tools and kind of the supporting software for all that. Maybe you want to operate down at the system layer. You know, that's where you know, companies down here, that's where companies like VMware and Red Hat, they've all kind of operated at that system software layer. Big companies, right? IBM bought Red Hat for $40 billion, right? $42 billion, I think. Networking software, tremendous opportunity there. And then, as I mentioned earlier, kind of programmable silicon. But you can kind of go work in different aspects of the cloud. You could be an engineering person who actually helps kind of design how these clouds are being put together. You could help operate the cloud itself. You might get involved in the security side of things. There's a whole bunch of different roles, and look at all the different places you could kind of apply those skills. You could do it by working for a cloud service provider or a network service provider or a managed service provider. When I say that, I mean somebody who's going to help assemble some of the piece parts to deliver a service. Usually that's what the managed service providers do. You might go work for a company like Airbnb, one of these cloud native enterprises that kind of delivers everything they do via the cloud. Or you might go work in enterprise IT. I think there's going to be tremendous opportunity going into large Fortune 500 type companies and bringing kind of that cloud engineering mentality into those organizations. You could go work for a solutions integrator. These are the guys who kind of, again, assemble solutions for big corporate IT organizations. You could go work for a company that develops software. You could work for a company that builds equipment. There's even opportunities, I think, working for the merchant silicon suppliers, right? You might want to become a participant in one of the open source communities. You could actually do that right now today from UMass. If you wanted to go in and develop code in one of these open source communities, as long as you can hack it, they'd be happy to have you. Of course, academic research. I just laid out probably 20 different areas of potential research for folks. And then, like I said, big data, machine learning, AI, wide open. And then I didn't really talk about security. There's tons of opportunities for security. The number one thing that has people freaked out about moving stuff to the cloud is security. And that comes through over and over and over again, and just about anybody you ask in terms of what's a barrier to adoption. Security is always the number one barrier to adoption. So the last thought I'll leave you with is you're in school, taking a lot of courses, everybody's working hard. The bad news is when you graduate, that never stops. You might not have to take as many tests, and you might not have to write as many papers or stuff, but I'll tell you, if someone who's been doing this for 40 years, you never stop having to learn, right? You never stop having to, put your nose to the grindstone and figure out what's going on so you can get your job done, whatever that happens to be. So what I always tell people is college is a great place to learn how to learn, because when you finally go out into the world and work, you're going to suddenly decide you're just going to continue to keep learning. A friend of mine just got hired by Amazon. So he's kind of my age. He's been around for 30 some odd years himself. And he said, he goes, I got hired by Amazon. They just put him through like a massive 90-day, immersion training program, right? I mean, he said it was just brutal. He said he had to just completely come up to speed on, a whole bunch of aspects of what they do with Amazon Web Services. And that's, I think, just kind of par for the course these days. You're constantly learning, and not only that, you have to learn how to learn by yourself. That's the other part. It's helpful to learn, with your peers and friends and things like that, but you also have to kind of blaze that trail yourself. So with that, do we have any questions? Yeah.
So I know we didn't talk about security much, but when it comes to the smart city and the smart industrial IoT, it seems like there's a big space for customizable hardware security solutions to prevent people from running the centrifuge up in the way that it's supposed to be run. That could make it simpler. If you're trying to just make unauthorized access impossible at the other layer, it seems like that might not guarantee you the same things you could get. So is there a space? Are there words for this? People use to describe that area.
I'll turn it around the other way. I always think about security as a multifaceted problem because you have multiple threat. You have multiple exposures to threats. That's the problem, right? And so there's physical threats to security. Like if I can get my hands on something, I can mess with it. So even if you don't have physical access to it, then you have ways you can mess around from the software perspective. There's even now ways we've discovered, right, that there's exploits in the way the pipeline operates inside these Intel processors, right? So you can actually inject code in these things that can actually hijack the system literally from the, execution level, that kind of blows my mind, but you can do it. It's because of the look-ahead stuff that they do in the microcode. But I didn't make this talk about security because I think there's so many kind of possible threats and so many different exposures. It's just a whole domain and kind of career unto itself. So the guys that I work with who do security, I mean, they walk around with a kind of a heavy load on their minds because they're always worried about so many different things that can possibly go wrong. And some of them are actually the stupidest, easiest things to prevent that are sometimes the most disastrous. But there's also some really clever and crazy stuff that you have to defend against as well. But I will say you this, Anybody who wants to go work in security, you'll have job security. No pun intended. Yeah. Someone else must have a question about something I've talked about. I raced through this so quickly. Yeah.
Yeah, so now like they're like little big data centers, and like maybe in the future there'll be like more smaller ones. Do you think those small like data processing centers like maybe one day sit in our homes for our personal use?
So I think, so the question is, will we have, smaller data centers in the future? And I think we will, and I think we'll have them for multiple reasons. Like, one is, if you think about the whole IoT problem, right, you're going to want to put processing and storage closer to where the data is being generated. There's no reason you're going to want to have to take that and move it all the way up to the cloud over here and then process it and then send it all the way back down over here. So I think for things like real-time IoT, I think you'll see a second tier of cloud infrastructure emerge that will, sort of distributed data centers, if you will. They'll be built off the same architecture. I think they'll have the same internals, but they will be smaller scale. And the other folks that will do that are some of like the communication service providers. They're going to take all these central offices that we have all over the place, and they're going to convert them into little cloud data centers. Because you're not going to have copper pairs going into them anymore, and class 5 switches. They're just going to be communication hubs, if you will, and they might have IoT data going into them. So.
Yeah, so these cloud providers are charging people for like computing resources. How do they do that? Is it by like power consumption, or is it?
Yeah, so that's a great question. It's like, how do these guys charge? So that's actually kind of the really interesting conundrum, I think, in the cloud is, I want to move my stuff to the cloud, but then when you look at all the stuff you're going to move there, the amount of code, the amount of data, and then you start looking at what the bill might be, then you might go, well, gee, I'm not so excited about doing that. So it's actually a little bit of a conundrum today. So again, if you're like a startup in Kendall Square that's trying to do a new mobile app, it's kind of a no-brainer to go to the cloud. You're a big business that has already a massive customer base, all kinds of applications, and a ton of data you have to support. You're going to do the math on that really carefully. And I work with an organization of enterprise IT executives who are kind of concerned about that problem, right? Is it going to cost me too much? Right? Even though I benefit from no longer having to own and operate my own infrastructure, still is moving it all from my private data center to the cloud ultimately going to make sense financially? So there are some cases where the jury's still out on that. I think there's some cases where it makes sense, and there's other cases where you might say, well, maybe not yet, and there's other cases you might just say, I'm just not going to do it. Which is why I think you'll still see a lot of that private cloud stuff being built. But it will build, the nice thing is if that's built to look like the cloud, if somebody offers attractive pricing, you can just take what you have in your private cloud, move it to the public cloud. Just like a week or two ago, Oracle came out with a pricing attack on Amazon. Oracle just came out and said, whatever Amazon's doing, we'll do it cheaper. And so that's actually a good thing, because that tells us we'll see some price wars going on here. But they charge by things like, how much CPU cycles you consume, how much storage you consume. Serverless is just this notion of you got some code that's going to execute, and you just get charged by how often that code executes. Like I said, it's kind of like time sharing. But the whole business model for the cloud providers, it's worth studying that. It is interesting. And there's a lot of trade-offs, I think, that go into that. There's a whole subject that the IT executives will call governance, which kind of falls in this area. Because then you can do stupid things like, well, we were testing a new load of the code, it was late Friday night, we stuck it up in the cloud, we let it run, and then we went home and forgot to turn it off. And then you found out the damn thing ran for the next 3 days over the long weekend, and then you come on Monday and you get the bill. So there's things like that you have to worry about. And there's definitely people who have shot themselves in the foot doing that. Wasted thousands of dollars or worse doing something like that.
So there's a data center in Holyoke that was built, within the last 5 or 8 years that I think is put together by, 5 universities there. And are you familiar with that?
I've heard of it. I've actually wanted to see it. But I can't remember who built it and actually what they're doing inside of it, but I'm aware of that.
It's like MIT, maybe Harvard, I don't know.
Right.
MIT, Harvard, Northeastern, UMass,
Okay.
BU,
Right.
And the state.
and the state.
Yeah.
Because I'm trying to understand where that fits in. That's not really the cloud, right? It's kind of their own private.
I bet you it's built off a lot of the technologies we just
Yeah.
talked about, though. I mean, especially if it's that set of players. I do remember reading about that, and I remember saying, "Oh, gee, that would be cool. I'd like to learn more about it." But I
And I
never.
went on a tour with the IEEE. The amazing thing is it's in a section of Holyoke where there used to be old paper mills in there.
Right.
At that footprint, there was probably, 10,000 people working there.
Right.
So we asked how many people work there now, he said 7, and that's the 3 shifts. So.
Yeah, yeah. Well, that's the amazing thing about these things, right? You don't need a lot of people kind of working inside the building. You might have a lot of people that are kind of connected in and monitoring what's going on, but the number of people that need to be in the building is fairly low because there's not a lot of monkeying around with the equipment that goes on. It's interesting, right?
And it was very modular, it's like you said,
Yeah.
they can just drop in a whole nother section and just.
Yeah, they just scale by racking in a whole new pod. And they just forklift and a whole new pod, drop it in, cable it up, you're off to the races. Yes?
So like, for certain applications like gaming, there's a need for like incredibly fast wireless networks. So when they're building these platforms, do they keep that in mind, like the networking side of it, do they keep that in mind, or is there a need for a shift in like the spectrums and the charters for like better household internet connectivity for this?
So to answer your question, the network is always a problem, and particularly the wireless network, right? So the big thing that's happening in wireless, and I haven't touched on this at all, is we're going to 5G, right? So 5G is like another order of magnitude increase in connection bandwidth. And so that's going to be a big game changer, and I think it will be a supporting technology for some of these IoT applications I talked about, right? And the thing about 5G is you could get, multi-gigabit connections, no problem, right? It'll be for both mobile devices that are actually moving around and also for like fixed devices, right? You might have a 5G connection into your home because, you can't get cable and you can't get Fios, right? And you live in a place where it's going to be hard to get, high-speed physical connection. They might be able to just, beam you essentially a 5G connection into your home. But my experience with this whole cloud computing thing is the network's always a problem. You can never have enough bandwidth. And, and then the thing is, as soon as you get more bandwidth, you start consuming it, and then you want more. So we're going to be on, I think, a continuous. I doubt whether we're ever going to get a point and say, that's enough bandwidth. I don't think we're going to get there because as soon as you think you've got enough, somebody's going to come out with some holographic 3D projection thing that's going to be the most amazing thing you've ever seen in your life, and that's going to consume, 50 gigabits of bandwidth or something like that, and everybody's going to want to have it. So to answer your question, bandwidth's always a problem, and wireless bandwidth in particular is going to be a problem. When, I don't know, but I'm pretty confident that it's not like we're going to say, oh, gee, remember we used to worry about bandwidth? I don't think that's ever going to go away.
Are there systems for kind of automating, making these systems more efficient in terms of like the resources that they're using in the cloud that don't require having an engineer go back and look at the code? Are there like abstract systems for making these things more resource efficient?
Yeah, I think resource efficiency is a little bit less of a concern than dealing with painful things like obvious bottlenecks or just shortages of capacity. So I think the focus today is, okay, let's always make sure we have enough capacity. Let's make sure we can identify where there's bottlenecks in terms of bandwidth and have systems that give us immediate visibility into that so we can rectify the problem. I'm not so sure anybody's at the point where they're really worried about optimization yet. However, that's not to say that that's not important and that at some point you'd want to address that. But I'll even say in networks, we've been talking about algorithms to optimize networks for a really long time, and guess how we work around that? We just make the network go faster. And I think there's an element of the cloud where that's probably the same thing. Maybe it's just cheaper to just bring in a whole, pallet full of more pods, hook them up, and call it good than worrying about how to optimize what we have. Now, having said all that, the tools that are used to deploy the application code and to kind of monitor the application code and update it and the stuff that happens in the supporting infrastructure to auto-scale the workloads and things like that, there's tons of tools that do that stuff. They're not necessarily, though, focused that much on optimization or efficiency, at least as far as I know. I just don't think we're kind of there yet. Yeah.
With more and more services moving towards cloud-based applications, do you see that problem with you servers be running more and more? Is it a problem of energy consumption available to those servers, or just the speed at which those servers can provide those different applications?
Well, just on energy consumption alone, that is a big deal, right? So having processors that can consume less energy is important, given the fact that you've got buildings stuffed filled with thousands of servers, you know, with multiple CPU chips on them, with all these cores running that are blazingly hot, and then you throw GPUs in there. I can remember distinctly a few years ago working with some students who were looking at like a water cooling solution for data centers, and they went and talked to some people I referred them to, and the people I referred them to said, no one's going to need water cooling in a data center. Go away, you know, it's kind of a bad project. Well, guess what? Now you have GPUs going into these data centers, they're going to want to water cool them. So, you know, everything's kind of up for grabs in terms of engineering these systems. Power, cooling, reliability, security, automation. I mean, all of these things are problems that need to be continuously addressed and refined and kind of advanced going forward as we increase the level of kind of technological sophistication. So I don't know if that answered your question, but power is a big deal. Power consumption, heat dissipation is really the big deal. Yeah.
I don't have a good idea for, you know, how the data gets in and out of a data center like that. You said 80% is
Yeah,
in
yeah.
the data center. There must be just massive amounts of data that going in and out of it.
Yeah, so you've got, you know, a lot of these big guys have like their own big dark fiber coming in that they usually light up and connect to a router that they put in one of these co-location, I should say, inter-exchange points. So there's a company called, I'm confusing them with Equifax. No, it's Equinox. So there's basically a company that builds out these big data centers where you put all the routers and you bring all the optical connections, and that's kind of where you interconnect, you know, this cloud to that cloud, or this enterprise customer to that cloud. It's sort of, you know, the inter-exchange points, if you will. And there's a number of guys who do that. It's not just that company. But yeah, so what happens typically is you've got all the traffic kind of converging on these inter-exchanges, right? Which is a bunch of routers basically in a big data center. And you got all this cabling in between them. And yeah, and some of those optical connections that come out of that building go into the optical network and go to Google over here, or Amazon over here, or Apple over there. That's basically how it's all done. But the interesting thing is, you know, those guys are getting so much data out of those things. They're actually just lighting up their own dark fiber. They're not relying on AT&T or Verizon or CenturyLink to give them an optical service. They're just saying, you know what, as long as I got a fiber that goes from here to here, I'll put my own gear on the end and I'll deal with it.
So they're literally have their own fiber.
They're not only that, it's the fiber they're leasing, the dark fiber they're leasing, but they're putting their own optical equipment on each end. They're actually building their own optical gear.
So they don't dig a trench and run fiber. So
No.
The fiber's out there.
The fiber's out there. There's guys like Level 3 and a whole host of guys back 20 years ago started trenching and building fiber. But the thing is, they light up the fiber themselves.
So it's excess capacity?
Well, I mean, dark fiber, you think about how much bandwidth is on a dark fiber, right, with DWM. I mean, they're building their own equipment on each end of the fiber.
Okay.
And so, you know, they don't worry about interoperability or, you know, they're just like, hey, I got to get data from this inter-exchange point out to my cloud over here, and they kind of light up their own fiber with their own optical equipment. It's really cool. Again, they special build stuff. The funny thing is the cloud providers are starting to look like what AT&T looked like when I joined it 40 years ago, right? If you think about it, right? They were vertically integrated. AT&T built everything from top to bottom, right? They even designed transistors kind of along the way, right? So they could build circuits, right? But if you think about the cloud providers, right? They're kind of vertically integrating. They're building their own, they're not building their own CPUs yet, but they build their own servers, they build their own switches, they're building some of their own optical gear.
Right.
You know, so they're vertically integrating because they have the economies of scale to do that, which is, I think, pretty interesting.
Do you see a movement to ARM?
You know, I don't think ARM is that relevant inside the data center.
No?
But, I mean, I could be wrong, but I don't see that. I think ARM plays more in the, device arena, right?
Right, okay.
That's what I think. I'm not an expert in ARM, but you don't see it mentioned as much in the data center. But I will say, there are, like I mentioned, there are certain algorithms and functions you want to perform that the Intel architecture isn't necessarily particularly well suited to. So people are developing, I think, other architectures, if you will. I mean, I think we will see other types of silicon emerge inside these data centers. That to me just seems inevitable, right? Once you kind of know what the workloads look like and kind of what the application flows look like, you can build the supporting silicon for that. So who knows what the world will look like in 10 years? It's kind of hard to envision. Yeah.
If all computing is moving to these massive data centers in the cloud, what are some of the concerns for redundancy and how if one data center goes down?
Right. Yeah, so I think anybody who's putting applications in the cloud is going to need to deploy them usually in a redundant fashion in physically separate locations. So Amazon runs Amazon East and Amazon West, or AW East, AWS West, and people will put software here and they'll put software there. So if one of them goes down, the other one's still available. It's stuff that's as simple as that. You basically definitely want to engineer in redundancy. I don't know if the cloud providers will give you that as kind of a service out of the box. I'm just pure ignorance on my part. But most people that need that high availability will have to take some sort of physically redundant approach. Maybe even use Amazon here and Google there, or Microsoft over here. You might even do that. It could have something to do with geographic coverage and other considerations. But yeah, the whole kind of resiliency aspect of this is critical as well. And by the way, that's a big part of the whole DevOps model, is how you ensure resiliency at the application layer. Because the thing about DevOps, you have all these different microservices. You might actually have something that's running 100 different microservices, and then things stop working, and you don't even know why, right? Did the code itself break? Did the service that's supporting the microservice itself break? Did something break in the network? So there are a bunch of strategies that are involved in kind of resiliency at that microservice level. That it's still in kind of an open, I think there's best practices for how to do that, but it's not like a no-brainer for a problem to solve. I think there's a lot of thought that goes into that. So we're up on 5:30.
It is 5:30,
Yeah.
almost.
Well, I appreciate everyone taking the time to listen to the talk and everyone who gets to watch it on YouTube.
Thank you so much.